The Venturi effect. We're going to look at volumetric flow rate. And this movie is to help you understand how to use a spreadsheet to process the wind speed data that you get for various cross-sectional areas of a wind tunnel. You'll see that the wind speed here increases when the cross-sectional area decreases. What we have is flow rate, volumetric flow rate to be specific, that we have a wind speed coming through here and then we decrease the cross-sectional area, which means that the wind speed has to increase because the flow rate has to stay a constant. And here it's a volumetric flow rate where we take the velocity multiplied by the cross-sectional area. Now we'll be using a quantity called rho, or the density of air. And the density of air in Denver, Colorado is about 1.1 kilogram for every meter cubed. And what that means is if we take a meter by a meter by a meter, that volume right there will have a mass of 1.1 kilograms. Now we need to find the flow rate for each of these wind speeds with their corresponding cross-sectional areas. So we're going to create a formula right here, equals. That's how we start a formula in a spreadsheet, is with the equal sign. Let me zoom in a little bit here so we can see this a little better. So equals, we want to click on the wind velocity, and that types a reference for us, C8, and then use the asterisk for multiplication. And you can find that on the numeric keypad to the right, on the right side of the keyboard. And we want to multiply that wind velocity by the area. That will give us the volumetric flow rate. When we hit return, it registers for us the volumetric flow rate. Now I can take this formula and fill it down like this. I don't know if you saw what I did. Command Z. Oops, I did Command Z twice. So let me redo this formula multiplied by the area. If you put your mouse in the lower right, it turns into a solid plus sign. We don't want it right here because that'll move the cell. Okay, let me zoom in a little bit. When I put my mouse in the lower right, I get a plus sign. Okay. When I drag that plus sign down, it copies the formula. So now it's looking at C10 times A10, and here it'll be C12 times A12. Now there's an even shorter cut that I can take, and that is double click right here. If the spreadsheet sees to the left contiguous values, then I can just double click and it'll populate all those cells for me. Well, notice that the flow rate appears to be rather constant. It's not going up or down, it's kind of going up and down, but it seems to be about 0.04. What we'd like to do is find out how well this is staying the same number. Okay, but first, let's find the average flow rate. Equals average. And as you start typing, it's giving you some choices. So we can just choose average, and it creates parentheses for us. So now we want to take these cells and highlight them. And it writes the reference, D8 colon through D13. So let me do that again. Open parentheses. I deleted that accidentally. I click on the first cell and drag down to the last cell, and it writes the reference. So there's my average flow rate, 0.0409 meter cubed per second. Okay, that's the volume per second, volumetric flow rate. If I want to find the mass flow rate, I take the density of the air and multiply it by the flow rate. So we're going to say equals 1.1, and that's kilogram per meter cubed, and multiply that by our volumetric flow rate. And that will give us a mass flow rate, or how many kilograms there are flowing every second. The uncertainty, that's a sigma, a Greek sigma. The uncertainty would tell us how far away from the mean value, this average value right here, do 2/3 of all these data points lie. So how much wiggle is in this data? All right, and to find that uncertainty, the standard deviation, sigma, we're going to use this formula. We take the square root, hold on to your hat, the average flow rate minus each individual flow rate. When we take the average minus the first flow rate, we square it. And then the sigma here says add to that square the average flow rate minus the next flow rate squared. See, when we do that from I equals 1 to n, where n is the number of data points. Then once we have that sum, we divide by n minus 1, the number of data points minus 1. Boy, that's confusing. So let's just build it piece by piece. Let's take the average minus the flow rate and then square it. So we start with equals, and we click on the average value minus the individual flow rate. And I forgot, we need to put this inside parentheses. We start with equals, and outside the parenthesis, we want to do caret 2, shift 6, and then a 2. So I'm squaring the difference. And I hit return. So there it is. But there's a problem when I fill this down. And that is that this value, D15, is going to look at D16, D17, D18, D19. And we don't want that to happen. So we're going to lock in the 15 with a $sign. Okay, the D8 is fine because I want to do D8, D9, D10, D11, yada, yada, yada. So hit return, and then I'm going to fill this down again. Okay, so now there's my average minus flow rate squared for each individual flow rate. And to find sigma, I say equals SQRT, the square root of, now I want to sum, I want to find the sum, open parentheses, of all these cells, the average minus flow rate squared. Sum all those up. Okay, and I don't know if you saw, but I started a second set of parentheses for the sum, and actually I don't need that. That was silly of me. Then I want to divide that by, here's where I want to open a set of parentheses. The number of data points, so I'm going to say count, open parentheses, all of these cells, close parentheses, and then minus 1, because it's supposed to be n minus 1. Then I want to close a parenthesis for this count, and then I want to close the parenthesis again for the square root, and hit return. So you can see that 2/3 of the data fall really, really close to these values. We can increase this decimal here to see a little bit more. And so here I want to increase the decimal until I can actually see a value. And here, looks like I had the wrong number of decimal places. So 0.041, that's my average flow rate, volumetric, meter cubed per second, plus or minus 0.001. That's our uncertainty, how well we know the average flow rate. And if I take this uncertainty and divide it by the measurement, I'll get a 1.6% uncertainty. Now you're going to have another set of data at a lower fan speed. You're going to record the velocities. Then you're going to use the same formula here for area times velocity, where here's the velocity and over here is the area. But then for the standard deviation, oops, I forgot to remove it. Let me show you how to build it. We can build this quickly. Equals STDEV. STDEV, open parentheses. And then we just highlight all those flow rates and close parentheses, and it'll calculate them. So let me just throw in some numbers. 2.1, 2.2, 1.9, 1.8, and then we'll do 2.0 again. Okay, so it's showing me the standard deviation just with this simple formula, STDEV, and then highlight all these cells. What that formula does for us is the same thing that we built piece by piece, okay, over here. So I hope that helps you a little bit in using Microsoft Excel for your Venturi effect lab. Something we should have done right at the beginning is save the file. So after you open it, choose Save As, and then you want to make sure that you go into the desktop, okay, and give it a good name and just save it. It's a good idea to put your name right here, okay, so it distinguishes it from another class, and then just hit save. So there you go, Venturi effect, volumetric flow rate.